Now we're thinking about the energy that waves carry. We, we know that waves carry energy because if you imagine a piece of string, here's a little bit of mass on the string, and then the wave heads towards the string, towards that little piece, and as soon as the wave begins to pass through that piece, the little piece of string starts oscillating up and down. In other words, it now has kinetic and elastic potential energy that of the kind that we usually associate with an oscillating thing. It did not have that energy until the wave hit it. The wave continues to do work on that little piece of the string and continues to give it energy to keep that little piece of string moving. And similarly, if we're talking about a sound wave, a sound wave is just alternating regions of higher than usual air density and air pressure, followed by lower than usual regions of density and pressure. So here's a little air molecule. It's not perfectly stationary, but it's more or less in the same location, bouncing around. And then here comes a high pressure part of the sound wave, pushes the mass one way. Here comes the low pressure region, and now this is lower than usual pressure over here, normal pressure over here, so the mass gets pushed to the other side. And then the next high pressure pulse pushes the mass again, and then when the next low pressure pulse comes, the mass is pushed back the other way, so the mass keeps moving back and forth. It's now an oscillating system, so it has energy. It got that energy from the wave. And there are several ways in which we try to quantify the energy that's carried by a wave. First, power, which is just the rate at which energy is delivered to some mass or to some surface or some area. Just the total energy delivered to something divided by the amount of time it took to deliver that much energy. And to think about that, let's think of a three-dimensional wave, say a source of sound, and the sound wave expands in all directions, or a light bulb, where the light waves are expanding in all directions. We can visualize that situation by drawing wave fronts. Remember what a wave front is. It's the set of all locations that are at the same state when they're oscillating, at the same state as waves, as different parts of the wave pass through. For example, here's our source of sound, and it's the sound waves are expanding in all directions. But let's just look at a two-dimensional slice. If you look at one line emerging from the source, you'll see, think of this as kind of a snapshot graph. You'll see at any one point in time, here's a region of higher than usual pressure. Here's a region of lower than usual pressure. That's what the peaks and valleys on this curve will represent. And then here's the next region of higher than usual pressure. So, but if you look in other directions, you see the same pattern. The first region of high pressure, the first region of low pressure, the second region of high pressure, and then up here the first region of high pressure, the first region of low pressure, the second region of high pressure, and similarly if you make a path in that direction. So when you connect all the points that are at their first, the first region of high pressure, all those points will be represented by this circle. Remember, since waves are coming out in every direction, this is just a two-dimensional slice So this circle here is really just a two-dimensional slice of a sphere. The wavefront in this case is a sphere. All points on this sphere are at the first location with higher than usual air pressure, and all points on this bigger sphere are at the second place with higher than usual air pressure. And of course, if this is one region of higher than usual pressure and this is the next region of higher than usual pressure, you must have gone through one wavelength in order to get from here to the next state that is identical. That's what wavelength means, the distance from one state to the next one that is identical. So all of these wavefronts, spherical wavefronts, are expanding at the wave speed. So this little piece of the wavefront is moving in this direction at the wave speed, like I've got illustrated here. This piece of the wavefront is moving this way at the wave speed, and this piece on the inner wavefront is moving straight to the right at the wave speed. All points on all wavefronts are all moving at the same wave speed. So since all wavefronts are moving at the same wave speed, the distance between two wavefronts is always going to stay the same. It's always going to stay one wavelength. But here's the deal. Think of each wavefront as carrying some energy that it will give to air molecules to make them start to vibrate. No matter what the size of a wavefront is, it's always carrying the same, it's always got the same energy, no matter how small or large that spherical wavefront is. And the wavefronts are always traveling at the same speed, no matter how large they are, no matter where they are. So the points right here on this bit of this wavefront all pass through this location in a certain amount of time, and the comparable points here on a smaller wavefront will pass through this point in the same amount of time because all the wavefronts move at the same speed. So the rate at which energy passes through this big sphere is the same as the rate at which energy passes through the small sphere. If you imagined a sort of a sphere that's not perfectly thin but has a tiny little thickness of 1 millimeter or something, it takes a certain amount of time for each piece of this wavefront to move that 1 millimeter through that 1 millimeter, and it takes the same amount of time whether you're talking about this wavefront or this wavefront because they're moving at the same speed. So all the energy that passes through this big spherical surface, 1 millimeter thick, is the same amount of energy in the same amount of time passing through this smaller sphere that's 1 millimeter thick. So whatever sphere we're talking about, no matter how large or how small, the wavefront is always carrying the same amount of energy at the same speed. The same amount of energy passes through every sphere, no matter what its radius, at the same speed. So the power is the same everywhere. Same amount of energy passing by per unit of time, no matter how close or how far you are from the source. So power, the rate at which the source puts out energy, and that's going to be the same as the rate at which energy passes through any sphere centered on that source, stays the same. But another important number for thinking about energy in a wave, intensity, is different at different distances. Intensity is just power passing through some surface or landing on some surface divided by the area of that surface. So for example, For example, let's imagine each of these spherical wavefronts passing through a sphere of points centered on the source. The same amount of power passes by any sphere, no matter what its size. But so this doesn't change, but as you get farther and farther from the source, you're looking at spheres of bigger and bigger radius, so bigger and bigger area. This gets bigger the farther you get from the source, so this gets smaller the farther away you get from the source. And that's what's really happening when, as you stand farther away from a source of sound, the sound is weaker, quieter, and when you're farther away from a light source, the light is dimmer, weaker, because the intensity decreases as the area increases, and the area is increasing because as you get farther and farther away, you're now located on a sphere with bigger and bigger radius. So power passing through some sphere of points divided by the area. What's the area of a sphere? Area is, a sphere is 4 pi radius squared. Power stays constant no matter where you are. 4 pi is obviously a constant, so we have an inverse proportionality here. We have intensity equals power divided by 4 pi, in other words, constant factors, divided by radius squared. And that's the pattern for inverse proportionality. Whenever two variables are inversely proportional, they always fit into an equation that looks like this. One variable equals constants divided by some other variable. Y is inversely proportional to x, or y is proportional to the inverse of x. You could say it either way. The rule for inverse proportionality, as you've seen before, but it's one of those things that you might need a reminder. In inverse proportionality, when one variable gets larger, the other one gets smaller. And in inverse proportionality, when one variable changes by some particular factor, the other variable changes by the inverse factor. So let's look at a specific example of that. Just want to make sure I'm following my notes. So, imagine that we are, let's say, 1 meter away from some light source. And at that distance, 1 meter away, the intensity is, let's say, 10 to the minus 3 watts per square meter. Watts is our unit for power. Power is energy per time. Watts means joules per second. Unit of energy divided by unit of time. And then area, the unit for area is square meters, so units for power divided by units for area. That's the unit label for intensity. Now, let's say we move back so that we're now twice as far away. Just twice as far. We don't even have to know what R1 and R2 actually are. We know that we've moved twice as far away. So now we can invoke inverse proportionality to figure out what the intensity is when we're at the greater distance. So we know that because we have this relationship here, intensity is inversely proportional to r squared. Repeat this again, it is not inversely proportional to r, it is inversely proportional to r squared, because here's the form for inverse proportionality. And what this means here on the right hand side is that after you've lumped all the constant stuff together, whatever is left over is the variable that's proportional to y. So here, after we've lumped all the constant stuff together, what's left over is not r, what's left over is r squared. So intensity is inversely proportional to r squared. So when r squared changes by some factor, intensity changes by the inverse factor. In this case, how does r squared change? Well, we have to figure that out. We know how r changes. From that, we can figure out how r squared changes. So square this to see how r squared changes. The new r squared is just this squared. 2 squared, 4 times old r squared. So we see that this variable called r squared changes by a factor of 4. The variable that it's inversely proportional to, intensity, changes by the inverse factor. In other words, the new intensity is the inverse of this factor times the old intensity. When you got twice as far away, the intensity wasn't cut in half, the intensity was cut down to 1/4. Or in other words, 1/4 of that, or 2.5 times 10 to the minus 4 watts per square meter. And you should be able to think this through going the other way too. If you know how the intensity changes, can you figure out what the different distances are? Here we knew about the different distances and had to figure out the intensity. So let's imagine you got some particular intensity when you're 1 meter away from the source, and now you move back to a point where now the intensity is only 1/100th of what it had been. So that is, the new intensity is 1/100th of the old intensity. When one variable changes by some factor, the variable it's inversely proportional to changes by the inverse factor. So the proportional variable changes by the inverse of this factor, in other words, changes by 100. And what is inversely proportional to intensity? R squared, not r squared. So this means the new r squared is the inverse of this times the old r squared. And r squared changes by a factor of 100, so the thing that it's inversely proportional to, intensity, changes by a factor of 1/100. And from that we can figure out what the new distance is, how far away you had to go to get an intensity 100 times smaller. Just take this easiest, you just take the square root of that equation. R2 is square root of this times square root of that. And R1 was 1 meter, so times 10. R2 is 10 meters. In other words, we step back 10 times farther away, and that doesn't make the intensity go down to 1/10, it makes the intensity go down to 1/100th. Let's take another look at this rule here, just from a slightly different perspective. Let's imagine that you're shining a light beam on a screen, and the power and the light beam makes a spot on the screen. The power delivered to that spot is just dependent on what's happening at the source of the light beam, so that's not going to change. But you can either focus the beam to make a smaller spot or defocus the beam to make a bigger spot, changing the area, and that'll change the intensity of the energy deposited in that spot. For example, let's say the power in that light beam is 1 watt per square meter. So the intensity of the light delivered to that spot is just power divided by the area of that spot. Area of a circle, so pi r squared. Right, in this case, r squared is not a distance from the source, it's the size of the circular spot on the screen. But again, power is constant, pi is constant, so again, we have intensity equal to constant factors, power over pi, divided by a variable r squared. In other words, again, we've got the pattern for inverse proportionality. Variable equals constant stuff divided by other variable. Or now the constant stuff is power over pi, and again, the variable here is r squared. So let's say that's the power you get for a circle of a certain size. Now imagine we tighten things down and make the radius of the circle 1/10 of what it had been. New radius is 1/10 of the old radius. What's the intensity now? It's going to be a bigger intensity because we've decreased the area. We're squeezing the same amount of energy, but now into a smaller area, so the intensity is higher. In other words, that spot will be brighter. How much brighter? Well, intensity is directly proportional to 1 over r squared. So there's an inverse proportionality between radius squared and intensity. However radius squared changes, intensity changes by the inverse factor. So we're given how radius changes, we need to figure out how radius squared changes. And that's easy. Again, just like in the previous example, square this equation. New radius squared is 1 over 100 times old radius squared. So radius changes by a factor of 100, a factor of 1 over 100. So intensity changes by the inverse factor. That is, new intensity is the inverse of this. Inverse of 1 over 100 is just plain old 100 times the old intensity. The old intensity was 1, so the new intensity is 100. let's, one more example, kind of working it backwards. Let's say we defocus the beam enough to make the intensity drop by half. New intensity is half the old intensity. And the old radius of the original spot was, again, let's say 1 meter. What's the radius of the new spot? Well, meter's too big for a spot from a beam of light. Let's say 1 centimeter. 1 centimeter for the radius of the spot. But now, what's the radius of the new spot? The intensity has decreased, which means it must be a bigger area, so a bigger radius. How much bigger? Well, not twice as big. Let's work through this. Intensity changes by a factor of 1/2, so the thing that intensity is proportional to changes by the inverse of 1/2, 2. What is intensity inversely proportional to? R squared. So the new R squared, this tells us that the new R squared is just inverse of this factor times the old R squared. So what is the new radius? The new radius is the square root of this. In other words, the square root of this. 1 over square root of 2 times R1. R1 was 1 centimeter, so the new radius is larger. It's 1 times the square root of 2, or about 1.4 centimeters. Okay, that's how intensity works. The thing you might have noticed in the in reading is that when you measure intensity in watts per square meter, the range of intensities that different waves can have is a huge range. But we like to have some kind of a scale that has more manageable, smaller numbers. And for that, we invent the decibel scale. And the decibel scale is a so-called logarithmic scale. So again, we're thinking of logarithms just like we were when thinking about exponential decay of an amplitude in a damped oscillation. The rule for converting from intensity in watts per square meter to an intensity level, that's the term, intensity level in decibels, goes like this. Right, beta is just our symbol for intensity level in decibels, and it's 10. The prefix deci means 10 log of a ratio, and the ratio is the intensity in watts per square meter of the wave that we're examining, divided by some reference intensity, some intensity that we compare every other intensity to. This reference intensity is the quietest intensity that a normal, healthy human ear can hear, and that comes out to about 10 to the minus 12 watts per square meter. Now, remember what a logarithm is. A logarithm is an exponent. When we were thinking about the exponential decay of an amplitude, the particular logarithmic function that we used was the natural log, symbolized with ln. This is different. This kind of log like any log, is an exponent, but it's an exponent to a different base than what we saw before. It works like this. When we say that the log of x is y, what we mean is that this exponent, a log is an exponent, this exponent, which we give the name y, is the exponent to which you raise 10 in order to get whatever was in this slot. So that's all we need to establish an important pattern here in the logarithmic system. So let's ask first, how many decibels does the quietest audible sound correspond to? That is, if the sound wave that we're actually thinking about has an intensity equal to the quietest audible sound, 10 to the minus 12th, which is the value of I0, how many decibels does that correspond to? 10 log of the intensity of the wave, which is just 10 to the minus 12, divided by the reference intensity, which is also 10 to the minus 12. So what we have is 10 log of 1. And then remember what the log is. This is the exponent to which we raise 10 in order to get whatever is in this slot. So, to what power must we raise 10 in order to get 1? Well, anything to the 0 power turns out to be 1. That's how we define the 0 power. So the exponent to which we raise 10 in order to get that is 0. So the number of decibels in this case is 0. Right? The 0 level on the decibel scale corresponds to the quietest sound that a human ear can hear. A dog, for instance, can hear something even quieter, maybe 10 to the minus, sound wave with an intensity of 10 to the minus 13. So how many decibels does that correspond to? Well, do the same rule again. The decibel level is 10 log the intensity of the wave that we're thinking about, which in this case is something that only the dog can hear. Humans can't hear because it has an intensity less than 10 to the minus 12, 10 to the minus 13, divided by 10 to the minus 12. Well, this number is smaller than this number by a factor of 10. This number is 1/10 of this number. So this fraction here is actually 1/10. Or 10 to the minus 1. And then what is the log of 10 to the minus 1? Log is an exponent. This log is the exponent. This log is the power to which we raise 10 in order to get that. So to what power must we raise 10 in order to get 10 to the minus 1? Minus 1. 10 times minus 1 minus 10 decibels. You can't have negative numbers on the decibel scale. You will have negative numbers on the decibel scale. So what have we got here so far? When the intensity is 10 to the minus 13th watts per square meter, the number of decibels that corresponds to is negative 10 decibels. And when the intensity was 10 times stronger, 10 to the minus 12 watts per square meter, the decibel level was 0 decibels. So a pattern's starting to emerge here, and we'll see it if we do just one more of these. Let's say now the wave that we're thinking about has an intensity not of 10 to the minus 12, but of 10 to the minus 11. In other words, an intensity 10 times stronger than this. So, number of decibels is 10 log intensity of the wave, which is 10 to the minus 11, divided by the reference intensity, 10 to the minus 12. The numerator is 10 times larger than the denominator, so this fraction here is equal to 10. So we have 10 log of 10. Log is a power. It's log of this log. This log is the power to which we raise 10 in order to get that. To what power must we raise 10 in order to get 10? Obviously, 10 to the 1 is 10. So, in this case, plus 10 decibels. Now we see our pattern. For the intensity of 10 to the minus 11 watts per square meter, the decibel intensity level was plus 10. And now look at what's happening. Every time the intensity gets 10 times a lot stronger, whenever the intensity changes by a multiplying factor of 10, say going from 10 to the minus 13 to 10 to the minus 12, you add 10 decibels. This intensity is 10 times stronger than this intensity, so this decibel level is 10 plus this decibel level. And similarly, in jumping from here to here, this intensity is 10 times stronger than this intensity, so this decibel level is 10 decibels plus this intensity, 10 decibels more than this intensity. And just as this was 10 decibels more than this intensity. Handy rule. Every time the intensity in watts per square meter gets 10 times stronger, you add 10 on the decibel scale. And then when you look at the a table there in chapter 15, you can see that condenses a huge range of watts per square meter intensities down to a much smaller range of numbers, much more manageable, conceptually easier to think about range of numbers. So the trick is often converting between intensities in watts per square meter and intensities in decibels. You'll try some of this in the in-class work, but let's look at one example right here. So when you're in a band or an orchestra, the loudest instrument, or the instrument that's capable of playing the loudest, is usually a trombone. And let's say that you're sitting in the clarinet section, just immediately in front of the trombone section, so that if one of the trombone players is playing a solo and playing quite loud, the intensity of the sound wave that you hear will be something like, call it the intensity of one trombone, will be something like 10 to the minus 5 watts per square meter. And it sounds like a really small number, but when you're right there in the band, it's a loud noise. First of all, what's the decibel level corresponding to the intensity of one trombone? Go back to the rule and do the same thing that we've done in those previous calculations. 10 times the log of the intensity of the sound wave that we're interested in, 10 to the minus 5, divided by the reference intensity, 10 to the minus 12. The numerator here is a factor of 10 to the 7th greater than this. 10 to the minus 5 divided by 10 to the minus 12 is the same as 10 to the minus 5 times 10 to the plus 12, right? Remember, if you change an exponent from positive to negative, you flip it from denominator to numerator, or numerator to denominator, as the case may be. So, and then when you've got the same base to two different powers and you're multiplying them, this is just 10 times the sum, or 10 to the 7th. So what we have in this case is an intensity level of 10 log 10 to the 7th. And this is easy, again. You don't need, we still haven't come across any case where you actually need your calculator. You just need the definition of logarithm. The definition of this logarithm is the power to which we raise 10 in order to get whatever is in this slot. To what power must we raise 10 in order to get 10 to the 7th? Obviously, 7. So 10 times 7, 70 decibels. Now, let's imagine more than one trombone playing. Like in the old musical, The Music Man, imagine 76 trombones playing. First of all, what's the intensity in watts per square meter of 76 trombones? Well, we'll imagine that they're all playing exactly the same way. Each individual trombone is putting out this much power per square meter. Well, then if you have one trombone putting out a certain amount of energy at a certain rate, and the second trombone player is playing exactly the same way, that person will be putting out the same amount of energy at the same rate. Or in other words, they'll both be putting out the same intensity. So two trombone players will give you a total intensity that's just twice that, and similarly 76 players will give you a sound intensity that's 76 times that. So the total intensity then is just 76 times that. 76 times 10 to the minus 5, or to put it in proper scientific notation, 7.6 times 10 to the minus 4 watts per square meter. And then do the same thing again. Use the decibel rule to find out how many decibels this much louder sound from 76 times as many sources sounds. And for that case, we'll actually have to use our calculators and also use a useful little rule. The rule goes like this. For any kind of a logarithmic function, whether it's this log log function or the natural log function that we saw a few days ago, the same thing is true. Log of a product equals log of one factor plus log of the second factor. And if this were a math course, I could show you why this is true. Basically, it's true simply because of the fact that a logarithm is an exponent. And then you use facts that you learned about exponents back in algebra class to demonstrate why this is true. But we'll just use this instead of worrying about why. We want to use this because, in this case, when we use our log rule for the decibels, we will have a log of a product. So here's what we have. The decibel level for 76 trombones is 10 log ratio of the intensity that we're interested in, which in this case is 7.6 times 10 to the minus 4, divided by the reference intensity, which is 10 to the minus 12. And so we've got three factors here, 7.6, 10 to the minus 4, and 10 to the minus 12. So let's lump the factors together like this. This quotient here, 10 to the minus 4 over 10 to the minus 12, is equal to 10 to the 8th. This numerator is a factor of 10 to the 8th larger than this denominator. So we can now rewrite this this stuff in here just a little bit more simply by combining these two into one factor. 10 log 7.6 times 10 to the 8th. And of course now we have log of a product, so we'll use this rule. So we have 10 times log of a product, and log of a product is log of one factor plus log of the other factor. And this one is easy, just as easy as the other ones, because this log is the exponent, a power. It's the power to which you raise 10 in order to get that. And if you want to, 10 to the 8th, 10 to the 8th, 10 to the 8th. And the power to which we raise 10 in order to get 10 to the 8th is obviously 8. So that's 8. And then here, for the first time, you need to actually use a calculator to tell you what the log of 7.6 is. And turns out that'll be about 0.88. So you've got 8.88 times 10, or 88.8 decibels. Which makes sense. Remember, one trombone had an intensity of, one trombone had a decibel level of 70 decibels. Well, if we go from one trombone to 10 trombones, we've increased the intensity in watts per second by 10 times. Each trombone puts out the same amount of energy, so 10 trombones have 10 times the intensity of one trombone. So when we go from the intensity of one trombone to the intensity of 10 trombones, the intensity is increased by a factor of 10, And remember, whenever that happens, you add 10 decibels. So that would take us up to 80 decibels. And then if we did that again, another 10 times as many trombones, so now 100 trombones. Again, we will have multiplied the intensity in watts per square meter by 10. 10 times as many trombones here as here, and if every trombone player is playing exactly the same way, the output of energy is 10 times greater here than here. So going from this step to this step, intensity in watts per square meter is increased by a multiplying factor of 10, which means, again, you add 10 decibels. So for any amount of trombone players between 10 and 100, the decibel level will be between 80 and 90. And that's exactly what we've got. For our number of trombone players between 10 and 100, 76 to be precise, we get a decibel level that is between 80 and 90. Just as we would expect by all this thinking here, where we looked at the simple increases in intensity. All right, for other this happens not just with sound waves, but with all kinds of waves, because all kinds of different waves can carry an extremely wide different range of energies and have an extremely wide different range of intensities. And what we like to do generally is squeeze that huge intensity in watts per square meter down to a more manageable range by using a logarithmic scale. The scales that we use for intensity level of earthquakes, for example, are also logarithmic scales. And in class, we'll take a little bit of a look at some of those also.